All right, guys. So lesson 5.4, non-linear relationships. Ooh. All right. So we've been talking about linear relationships and emphasizing that this entire time. Now we're going to talk about, well, what do you do when it's not linear? All right. And this actually requires a little bit of math, algebra 2 background. So I don't know who your algebra 2 teacher was. Leong is the only person I think that was in my class for algebra 2. But let's see what you guys remember. All right, so flashback. Log of 100. Okay. Does anybody remember how to simplify that? Log of 100. Just throw it out.
At 1.
Oh, close. It's not 1. But it's very
2.
close. It is 2. Good. And why is it 2, Billy?
10 to the power of 2.
Exactly. All right. So when you do log of 100, there's this hidden 10 base down here. And basically it's asking 10 to what power gets me the 100. All right. And that's what log is. It's asking what is the exponent? What is the exponent? So the answer is 2. All right, good. Let's try the next one. ln of e, the natural log of e. Does anybody know the answer to this one?
It's 1.
Ooh, good job, Billy. Who was your algebra 1 or 2 teacher?
Weitzman.
Good job. Oh, Weitzman.
Yeah.
Yeah, I loved Weitzman. She was an amazing person. All right, so this is the natural log. It's base e. All right, e is like a special number, kind of like pi is a special number. E is a special number. E to the first power is what gets us e. So that answer is 1. All right, good. Let's try a different kind of problem. This time, solve. And you need your calculators for this one. All right. So for this one, it says solve log of what gets me 5.4. All right, well, we know again, if it doesn't have a base, the understood base is 10. So it's asking 10 to the 5.4 exponent is equal to what? All right, so if you look back at number 1, right, that's the same kind of setup, except our unknown is actually now in the log. So 10 to what power, or sorry, 10 to the 5.4 power is equal to x. So hopefully you guys know how to do that on your calculator. Double check and make sure you know how to do 10 to the 5.4 power on your calculator. And you should be getting 251,188.64. And I'll stop at that decimal. All right, is anybody not getting that on their calculator? Okay. All right, let's try number 4. Very similar. This time we're asked to solve for the natural log. All right. So remember, the understood base for this one is e. So this means e to the exponent of 3 gets you what's inside that log. All right. So now try to find this on your calculator. E to the exponent of 3 is equal to x. And see if you can get 20.09. All right, does anybody need help finding how to get to the e to the power exponent? Yes? Okay. So where you go is you hit the blue button, and then you go straight down, and right below log, you'll see ln.
I just couldn't find where the button was. Okay, thank you.
You're welcome. All
Can
right.
you show me number 1 again, Miss Leong? I didn't finish writing it down.
Yeah, no problem. There you go. All right, guys. So as you can see, we are going to be using logs and possibly natural logs as well. All right, in our lesson. So I want to make sure you guys still remember how to use logs. And in fact, back in Algebra 2, you guys were probably wondering, like, where am I ever going to use this knowledge, right? When am I ever going to need to use log and natural log? Today's the day. We're actually going to use log and natural log in statistics. All right. All right, so here is the situation, okay? We've been handling scatter plots that are linear thus far, all right? And so using a best fit line has been easy because we have linear scatter plots. Today, we're gonna talk about what happens when we don't have a linear scatter plot, all right? So when the linear model is not linear, right? You might get something like this guy, right? With a residual plot that shows that pattern, okay? So we should not use the LSRL on a situation like this, okay? It's not a good idea. So what we do is what's called, we transform, all right? We transform the data, all right? And I'll show you guys how to do that. But what happens is, once we transform the data, it'll make it linear. Okay, so that's the goal. And the residual plot, you can see, is just random scatter. Okay, so that's the goal of today, to straighten out non-linear data. That's our goal today, to straighten out non-linear data. Okay. All right, so for linear data, right, we use the least squares regression line to find the best fitting line, right? For linear data, it makes sense to find a best fitting line. For nonlinear data, technically, you would model it with an exponential curve. And we could do that, and some statisticians do that. Instead of re-expressing or transforming data, they'll just find the best fit curve. That's a little beyond our scope of the lesson, all right? So that would take like maybe some calculus, which again, you guys chose to take stats for a reason, right? So instead of trying to fit the best fit curve, we are going to re-express our data, transform it, and straighten out the data. All right, so that's our goal today, okay? So our problem is that we can't use least squares regression for nonlinear data because the least squares regression depends on correlation, which only measures the strength of linear relationships. So our solution is that we will transform the nonlinear data into linear data to determine the best fitting line for the transformed data. Okay, so you'll see the words transform, also re-express is another term for it. All right. So that is our goal. Now let me show you how. All right, let me show you how. Flip to the back. All right, so this is the how. The ladder of powers. We're going to be using mainly exponents and logs to re-express the data. Okay. All right, so it's called ladder of powers because like a power exponent. Let me show you how this works. So let's say our y, right, is to the power of 1. This is our raw data. This is our starting point. Okay, this is doing nothing to the data. And let's imagine that it looks something like that. Okay, Let's say our y looks something like that when we graph it. Clearly not linear, right? So what we can do is we can walk through our ladder of powers here. So let's say we decide to square all the y values. And we graph it, and we see that it did this. Okay, it got even more curved. What that tells me is that I went the wrong direction on the ladder. Okay, sometimes that will work and I'll straighten it out, but sometimes it'll make it even worse. So if it makes it worse, that means, oops, instead of going up the ladder, let's go down the ladder. All right, so let's do y to the 1/2. Now, I don't know if you guys remember this, but y to the 1/2 is just equal to the square root of y. Okay, so it's the same thing. So square root of y. And let's say I make the scatter plot and oops, it's a little less curved, but it's still a little bit curved, right? So it's a little less curved, but there still is a curve there. Well, that's a good sign because that means, okay, I went in the right direction, right? But I'm still not there yet. Okay. So let's say I'm getting impatient and I'm like, oh, okay, I'm going to skip. I'm going to try to get it right on the linear one. So I decide to do y to the negative 1/2. And let's say when I make the scatter plot, it ends up looking like this. Okay, so that tells me, oops, I went too far in the ladder. So now let's backtrack back up a step on the ladder. And I have this 0 in quotes. I have it in quotes because I don't actually want you to take y to the 0 power. Because what happens when you take any number to the 0 power? It becomes what?
1.
Yeah, it becomes 1, any number. So don't do that because that basically destroys all your data. Instead, this is the log of y. This is the log of y. And that's that middle step between y to the 1/2 and y to the negative 1/2. And what this would do is this would straighten out our scatter plot. And that would be, in a sense, the winner. Because that's what we want to see, right? We want to see that linear, straightened out scatter plot. All right, and just to complete this, y to the negative 1/2, if I decided just to go all the way there, this would end up being an even more curved scatter plot. All right. So honestly, guys, it's a little bit of trial and error, right? But know that how it affects the scatter plot, right? It goes based off of the ladder, right? The further down the ladder, the more the effect is, okay? So it's kind of trial and error, but educated. All right, any questions about that? Okay, let's try it out. So grab your calculators, practicing case number 1. All right, let me pull up my calculator. So go ahead and start typing in L1, L2, your very first example. All right, so just focusing on L1 and L2, okay? The first thing you wanna do is just kind of look at what the scatter plot looks like without doing anything to it yet. So go ahead to second stat plot. And I'm going to turn on my scatter plot. And I want to do L1 and L2. Now to get to L2, I'm going to go second and the number 2. All right, so the blue button and the number 2. And that's how you get to all your lists, L1, L2, L3, L4. All right, let's zoom number 9. And that is your scatter plot. All right, so I don't know about you guys, but I definitely see a curve there. If you're not convinced, you can always check the residual plot, but that takes a lot more buttons to push, right? You have to do lin reg and then graph the residual. But I definitely see a curve. So I'm gonna start going around in my ladder of powers. Okay, so let's try the y square. Okay, let's see what direction I should go. Well, actually, okay, maybe we'll try going down the ladder since there's more options that way. Makes more sense. All right, let's go square root of y. So watch carefully. This is what you're gonna do. You're going to, oh shoot. Okay, so go stat, edit, okay. Really quickly, ignore what I'm gonna do right now. I'm gonna clear out my L3. I actually need space in my L3. Okay. So make sure L3 is clear, don't delete. All right, so press clear to clear out L3. And we're gonna play around with the Y coordinates. We're gonna play around with L2 in L3, okay? So go up to L3 and you're gonna go square root, all right, of L2. So second 2. We're gonna square root L2 and then press enter. And it does all of it for you right there. Okay, let me take a pause. Questions?
It gives me an error when I try to do it.
Make sure that you highlight the L3 and not the cell below L3. All right. Did that fix it, Karis?
Yeah.
Yeah. Okay, cool. All right, so now let's go ahead and graph L1 and L3. All right, so go back to second stat plot. And now we're going to graph L1 and L3. So second 3, we'll put L3 there. Zoom 9. All right, looks pretty good, right? Would you guys say that looks linear or do you guys still see a curve?
It's like fairly linear.
It's fairly linear.
I mean, like the bottom curves like a tiny bit, but not really.
I agree. I actually do see a little bit of a curve there. Just a
But just like that first point is like a little higher up. So I feel like that would make it linear.
I agree. So because of that, I'm gonna maybe go down one more step in the ladder just to test it out. If it looks even better, then I would go for it. If it doesn't look better, then I would stick with this one. All right, so this is looking pretty good, but like Kira said, yeah, I definitely still see a little bit of a curve. So let's go back to stat, edit, go back to L3.
Leong,
Yeah,
if we saw that on a test, we'd still put linear, right?
say
Or
it
like a line like that. Would you still consider that line to be linear? Like if we saw it, or like we saw that on a calculator for a test?
No, because basically there is one correct transformation that would make it the most linear. So you guys need to find which one makes it the most linear, and everybody should have the same answer if they get that problem.
So out of the 5 steps, there's always one that's just way better than the others.
Exactly.
Okay.
Yeah,
Okay, thank you.
good question. All right, so let's clear out L3. So I'm going to press clear, enter. And let's go down the ladder one more step. All right, so this is the log. So I'm gonna go log, which is right next to the 7 button to the left. And then second 2 to put my list 2 into the log. And this is why I play around with L3, because I want to keep all my original Ys in L2. All right, press enter, and hopefully you guys are seeing these numbers. And then let's go back and graph L1, L3. Everything's already set, so just hit zoom 9. And I don't know about you guys, but I think that looks better, right? That looks very linear, yeah. So a couple things you can do if you wanted to double check. If you wanted to try the next step just to see what would happen, you can definitely do L2 to the power of -1/2, and then graph that. Okay, and that looks more curved to me. So I know that, all right, that's going too far. So you can literally try all of them and just pick your best one. The other thing you can do, if you want to get real fancy, is you can even check the residuals. All right, so let me go back to my log. I'm going to do lin reg L1, L3. And then already, actually, I can see 0.99999. Okay. I don't even need to check the residual plot. That is almost a perfect line. So that's another way you can kind of like, just to like ease your mind to saying, yeah, that is the best one.
When you're like making the, like trying to see if it's linear or not, you only use like L2 to like when you're like, say that you're like square rooting L1, right? Wait, hold on. I need to rethink how to rephrase my question, and I'll come back to you. I'm like confusing myself even more. Give me 1 second.
My graph was curved.
Are you, okay, did you do L1, L3? Make sure you're not doing L1, L2.
Yeah.
Okay, and you logged all the L2s?
Yeah.
And you're getting all these numbers, the same ones as me?
No.
Okay, so then that's the issue. Make sure you are logging L2.
Okay, I figured out. So when you're like playing with the data, right?
Uh-huh.
L3, you only use L2, right?
Yes, correct.
Okay.
All right, Karis, how are you doing?
Oh, wait, I found it. I had the numbers for case 2 instead of case 1.
Oh, got it. Okay. All right, guys. So now hopefully you are convinced that logging is the best option. Okay, so let's go ahead and write down our answer. So let me share my iPad again with you. All right, so to write down your answer, what we're gonna do is we're gonna write the equation for the best fit line. All right, so it says find the least squares regression line right up there. Okay, so we're going to find that least squares regression line. Well, we found out that log, right, like x and then log of y was the one that worked the best, right? So now this is how you write your best fit line. Okay, so first off, right, on your calculator, okay, you need to go to lin reg to find the y-intercept and the slope. Be careful here. Make sure when you do lin reg, you do it with L1 and L3, right? The transformed y. So make sure when you do lin reg, you do L1 and L3. Okay. Now, when you write the equation, we typically will write, you know, balance is your y. The y-intercept I got was basically 2.0. and the slope was 0.0043 times your x variable, which is months. All right, unfortunately, this is actually not completely done. This is not correct because if I just give this equation, well, it doesn't tell you how you transform the data. So what you want to do is you want to make sure you show that this is the log of balance. That's your L3, right? That's what L3 is. It's the log of all your balances, of all your y variables. So this is your equation. All right, any questions there?
Wait, do you put b first and then like plus ax, or is it?
It doesn't matter if it's A or B. Look at what letter is in front of X. That's your slope.
Yeah, but like, cause on the calculator it like orders it differently. Where like the ax, that doesn't matter. for the
Yeah,
equation?
you put 0.4 or 0043 times months plus 2.
Okay.
Same thing. All right, other questions? All right, then the last thing is we're gonna make a prediction with this now for 100 months. So plug in 100, so log of balance, I'll just call it B for now since I'm running out of room here, of 2.0 plus 0.0043 times 100. And that gets me 2.43. All right. So now this is where that warm up hopefully will come in handy. So remember, log base 10, right, is understood. So that means 10 to the power of 2.43 is equal to the predicted balance. And that gives us a predicted balance of $269.15. And that is your final answer. All right, any questions? Okay, we don't have time to go to case 2, so let me just go ahead and give you guys the answer so you can use it for extra practice. All right, so the answer for case 2 would be the transformation that worked out the best was the square root of y. So this would be the square root of the predicted weight is equal to 0.5709 plus 1.6842 times years. And the prediction for 2 years was 15.52 grams. All right.